theoretical assumption upfront, and many of you will find it counterintuitive, and I will explain to you why I believe that. But let me go back to like a history of where I start. So this is a publication that this talk is based on, in case you want to take a look. It's in the like a review of general psychology in a recent, like a few months ago. So basically, let me tell you what I believed about the theory when I was younger, like 20 years ago. So because my training was in optics, basically physics, I wasn't trained as a psychologist, and also my mentors in psychology, Hal Pasher and Ann Treisman, they are both like very traditional, theory-driven cognitive psychologist. So for all those reasons, when I start, I have the strong belief that psychology should be like physics, even if it is not yet. I believe it should be. So at that time, my goal is building a theory that is simultaneously precise, broad, and simple. So those are all nice terms, and I will explain to you later why those three terms are particularly important. So my work in those period can be summarized as the Boolean map theory. It's a theory of visual attention, but it's not like a theory. It's not the main thing I want to tell you today, so I will just introduce it very briefly. So basically, in this theory, I propose that our conscious perception, we can only process one color at one moment. Like we can only see one thing at one moment, but we can see multiple locations. How to prove it? So by looking at those two, I'm sure it's very easy for you to verify that like the locations on the two in those two panels are exactly the same as each other. And if you pay attention, you will also notice that the colors in those are also exactly the same as each other, even if they do not map them on the same location. But you can always find one red here, one red here, one blue here, etc. However, the critical point is that to know the locations are the same, it's very easy. You can see that almost instantly. But to see the colors are the same, then it takes a while. You have to basically check them one by one: red, blue, yellow, green, etc. And that's why I mean, that's not the only evidence, but based on several such experiments, I propose this theory. We can see one color or one feature at one time, but we can see multiple locations. Okay, so that seems like a simple enough theory, and the evidence is straightforward. So at first, everything seems to going very well, and but then like everything changes. So let me tell you exactly what happened. So when I was still very optimal about this kind of approach, I saw no fundamental barrier between psychology and physics. So I was optimistic that the same scientific process would lead us to a grand unifying theory. Uh, of course, not a theory of psychology or theory of attention, but a theory of, for example, like a Boolean map would be like within reach. Like it should be unified, should give us a unified explanation for all the relevant experiments and findings. But that didn't work out. And that's not what you typically hear from a talk. Normally, people tell you it works out really well, but in this case, I tell you that it didn't work out. So what happened? Okay, so basically, when I look back, I divide my 20 years of exploration and failure as three stages. The first stage, is in which I try to reduce weakness. So back then, I already knew that a major problem of psychology is a weak concept, and everyone knows it. So I want to spend 5 years making the Boolean map theory more precise. My belief was that, just like in physics, once you make everything completely precise and concrete, all the irregularity on the surface would disappear. You would get a simple and elegant core of the theory. You would get something simple and broad and elegant and precise. However, contrary to my prediction or expectation, I found that increasing precision inevitably resulted in greater complexity. Basically, once I make things concrete and precise, I always found there are more and more factors, more and more detailed factors come into like a play. Then the situation become much, much more complex, and I couldn't really reduce it to any simple rules. So that's a major disappointment. And after some years of like not knowing what to do, I finally believe that what I should do is to pursue a complex theory. Basically, the lesson I learned from those periods is that my pursuit of simplicity itself was the problem. So because the reality is complex, and we couldn't cover reality with a simple theory. So it's simple, but it wasn't obvious to me back then. So to compare to physics, basically, I believe, and in most situations of the physics, you can get precision, breadth, and simplicity all at the same time. But in psychology, once you get precision and breadth, you cannot get simplicity. And to generalize this, I propose that there is something I call PBS, impossible trinity. So basically, I believe there are three critical attributes in psychological research, or perhaps more broadly, any social science or behavioral research: simplicity, breadth, and precision. Experimental findings are typically fragmented, and theoretical concepts are typically vague. So, in a way, we all know that, but at least back then, my belief that is that experimental findings are fragmented because we haven't done our best. Theoretical concepts are weak because we haven't done our best. Once we do better and once the field make progress, we will eventually get a perfect finding, perfect theory. But now I propose that is not true. There is a fundamental limit on those. So no matter how well we do, how well we try, we can never get that. And fundamentally, once you try to get something that's both precise and broad, it will become complex. Basically, you lose simplicity. And then for that purpose, you need a comprehensive exploration to review all those complex details. So comprehensive exploration is not just a general term. It is a term I propose as a specific method, which I will tell you. Okay. So basically, this is a PBS impossible trinity I propose, which is the foundation of today's discussion. Okay, you may ask why? Why this PBS impossible trinity? Of course, it's not something I can strictly prove. It's kind of like a conjecture or hypothesis. But I do believe it is true. And the reason why it is true is because a psychological process, like an elephant, is a complex entity composed of interconnected yet distinct parts that cannot be reduced to a single rule. So it's like the blind man and the elephant of the ancient India, like a story. Um, the elephant is complex by its nature, so you can't hope to cover the elephant with a like pillar theory or snake theory that can give a perfect explanation for the whole elephant. So it's a psychological process. Okay, so once we establish that we have to choose between those three options, then it is value-based judgment that I propose, I believe we should try to review the whole elephant. We should try to be both precise and broad, and we should give up simplicity. And that is means we should move away from the fragmented findings and weak theories which occupy our field for now. Okay, at this point, sometimes I hear comments such as that it is not nice or it is not good to try to hope that one approach will dominate the whole field. To be clear, I do not argue that should be done. But I do argue that this approach should occupy a decent portion of our research, maybe a quarter, 20%, something like that, which is essentially zero now. So I believe this should be expanded greatly. Okay, so going back to the history of my exploration. So once I draw the conclusion that I should pursue something complex, I try to embrace complexity. But it's not that easy. So I would build a complex theory. But I quickly found that insights from individual studies is impossible to integrate. So at first, all I hope is that, okay, I will do maybe 100 different studies. Just like in traditionally, they would be separate studies. And I try to summarize them together to build a complex theory. But then I found out it's impossible because if they're not designed with a unified format, then you can't really draw a unified conclusion because they're not comparable to each other. And after I spent 1 or 2 years to figure that out, and then I moved to a more systematic approach, which is what I call standardization. So what does it mean? Basically, I try to standardize the task and the stimuli across an extensive range of conditions to enable meaningful comparisons. So I will tell you one line of studies which is exemplify this. So in the Boolean map theory, I published this, which is a typical traditional study with a 2 stimulus types multiple 3 tasks. And I try to expand that to 16 stimulus types and multiply 8 tasks. And then I finally spent many years. I expanded to 16 stimulus types, multiply 26 tasks. To be clear, I covered all the combination of those, so that's hundreds of experiments, conditions. I mean, not separate experiments, but would correspond to one typical study. Anyway, I was really excited about this adventure, although it's terribly unproductive. Spent many years to produce those. That's pretty much all I got from those 7 years. But I was really excited. However, when I finished that, I look back, I still consider it's a failure. Why? Okay, first, why it's a failure? Because I tried not just one line of study, something like 5 or 6 different projects, but only one of them worked out. All the others, the situation is too complex. I couldn't summarize it into any simple framework, so I have to give up. And why that didn't work? And my conclusion is that there are 3 reasons. First is data size. I really needed tens of thousands of data hours, but I could only collect about 10% of that in the lab. And then verbal theories, they proved too weak to capture the necessary complexity. And then experimental design, it became impossible to manage more than 5 factors at once. I will elaborate on that later. And okay, all of those are terrible enough, but finally, the fatal blow that really make me to think, okay, this is not going to work. This is not what I want to do. Is a human factor. So what human factor? So basically, I spent many years work on this line of study. And I strongly believe that in theory, I made it much broader, so the scientific value should be much greater. And I still believe it now. This is much scientifically much more valuable than this and than this. However, I sent it to a group of colleagues. So when I did this back then, maybe almost everyone write back and say, okay, they really liked it, and some of them give some comments, etc. But generally, maybe some of them don't really like it so much in their heart, but it's clear that all of them read it, at least quickly. It's about 2,000 words brief paper in psychological science anyway. So, however, for this, I send it to something the same amount number of people or even more. And almost everyone write back and say, nice work. I will read it later. I look forward to reading it. But none of them write back. Exactly 0 followed up on this. And that made me realize, okay, once you've done something complex, nobody's going to read it. And that is reality. Greater complexity, less appeal. And so the ideal is that we value deep theories. The truth is our cognitive bias consistently rewards simplicity. So that's the point. I decided, okay, I have to give up what I have been doing for 20 years and to do something new. So what is that something new? But before I tell you that something new, let me explain a little bit about the curse of complexity. For this, many of you probably know better than me because it's originally from the literature in decision making by Daniel Kahneman and many others. So basically, the conclusion is that once you get something complex, people use simplified strategy to deal with it. And interestingly, as far as I know, all those researchers draw all these beautiful, interesting conclusions, but almost no one applied it to academia and tried to point out the implications. So I will just say it aloud here. So basically, because of the curse of complexity, in this area, once someone try to do precise and broad studies, and that is complex because of PBS impossible trinity, then they will suffer because the work is difficult to do. On the other hand, if someone do narrow or weak studies, then the work will be easier to do. And then if they try to do these precise and broad studies, even if they manage to finish the study, it's difficult to publish. And even if you publish, you couldn't get much credit because nobody is going to read it. On the other hand, if you do narrow or weak studies, people are going to read it, people will like it, the work is easier to do. So all in all, perhaps the biggest secret, at least I didn't find out after many years, even if I have followed that unconsciously, just spontaneously myself, is to something narrow or vague. Then you can be easily successful. You can get published in Science, as I did. It's a narrow study, so you can publish it in Science. But once you do a complex study, you couldn't. You have to publish at best in maybe JPHPP, something like that. So that's all in all the magic bullet of success in academia, as I said now, is to do something simple, which is either narrow or vague. So, but that's a sad story, but I cannot believe that is the truth. Okay, So how do we deal with that? I believe it's a very unfortunate situation that we have to do low quality, weak or narrow studies to be successful. And once we try to do precise and broad studies, we are doomed to fail. However, I don't think it's a problem that cannot be solved. I think the problem is that complexity induces so much burden, as all of you know better than me. And then once we reduce that burden, then I believe people do generally like precise and broad studies, at least they could. Then we will come back to the right solution. We will like uh, favor the more precise and broad study. But how do we reduce complexity? That's a key question. Okay, so I believe the critical point here is that we have been following physics as our model in psychology, and we should not do that. And we should follow AI because AI deal with complex and mental mechanisms. You may think, okay, another AI for science guy try to ask us to give up theory to build black box. But I'm not going to do that. That's the opposite of what I'm trying to do. So, but I do believe there is important lesson we can learn from AI, not building black box, but their basic rationale we should learn. Okay, to see what the secret of their success, let's see how they navigate the PBS impossible trinity, because they still have to deal with the same situation, the same problem. So basically, they use large-scale datasets to achieve breadth. They use quantitative model to achieve precision, and they cannot achieve simplicity, that's for sure. All their models are extremely complex. However, why is that not a problem for them? Because even if they cannot achieve simplicity, they can reduce the complexity induced burden using standardized benchmarking. And that is the key we will borrow today. Okay, let me explain why standardized benchmarking helps. Benchmarking cuts the burden of complexity with one powerful move. It replaces endless debate with a single objective metric. So basically, there is an objective metric. We know which model is better. That's how it works in AI. It's not perfect, but it's much better than what happens in psychology. In AI, a complex model's value is instantly clear from its benchmark score. We know in AI, for example, object recognition, they do have some recognition accuracy, which can tell you this model is better than that one. But in psychology, we have no such objective score. There are theories of object recognition. I mean, it's not hypothetical. There are real theories, such theories. And each of them are supported by various findings. But the debate is never over. We can only argue which one is more interesting or which interpretation is more persuasive. That's the best we can do. We can never convince each other or the audience. So that's why we never can deal with something complex, because we have to try to convince others by a simple story, which is the problem of everything. And so we should not be based on storytelling. We need to based on an objective benchmark score. What it makes worse for us is that in AI, even if you increase the scope of study for 100 times, you can still use the same metric, the benchmark score. But in psychology, if you try to increase the scope of study for 100 times, like what I tried to do, then it becomes a nightmare. People are not going to review it, people are not going to read it, and you easily get confused yourself. because all you can be based on is verbal theories, verbal interpretations. And suppose a paper you have to draw hundreds of conclusions. How is people going to understand it? Okay, so that's enough for the problem. Here is the solution I propose. So the solution I propose is what I call the comprehensive exploration approach. Basically divided into 4 steps. For design, we start with a stimulus-driven design. And then data collection, we run a large-scale experiment. And then analysis, we use exploratory iterative model building. The output is a quantitative information processing model. So that's for 4 steps. So in AI, researchers build a benchmark dataset and iteratively develop models until they achieve something remarkable, like NXNet from ImageNet. In psychology, we can do the same. We can build a dataset for decision making, benchmark dataset for decision making, benchmark dataset for working memory, and then we keep improving the model until we get a perfect model, and hopefully something great will emerge soon. That's what I propose. We call this the comprehensive exploration approach, or the CE approach. Okay, I should note that while the CE approach draws inspiration from the rationale of the AI revolution, it is also directly influenced by previous work in psychology and behavioral science, particularly that of Duncan Watts and Tom Griffiths. You probably know Tom Griffiths really well for his work in decision making. Okay, so let me get to the most critical point today. How do we do stimulus-driven design, and why do we need to do that? So the first step of CE approach is the most striking, stimulus-driven design. This means we must abandon traditional theory-driven experimental design. Let me explain why this transition is necessary. So why do we need to switch from theory-driven to data-guided approach? The reason is that precise and broad studies are inevitably complex and involve many factors. Then, traditional methods in psychology start with theory, requiring us to define all variables clearly from the beginning. Then we have a problem. It doesn't work. It's too complex. However, if we do a data-guided approach, AI methodology starts from data, eliminating the need to define all variables clearly from the beginning. Then it works. Okay, let me tell you an example from working memory. I will use this. This is recently published in Nature Communications. So I will begin by showing that in this example, the stimulus-driven design proves far more feasible than the theory-driven design. The latter is basically impossible. So basically, several years ago, when I tried to do this study from the traditional theory-driven approach, I reviewed the literature and compiled a list of all known factors. Of this, I don't want to elaborate on that, but simply it's a list of factors for working memory that's known to matter. After months of struggling, I had to surrender. I list only 5, but the total there something like 15. So you could say maybe I just wasn't skilled enough. Maybe someone better can do it. However, look at our entire literature. You will find 3-factor designs sometimes. You will never find a 10-factor design or 15-factor design or 20-factor design. That's simply impossible. Well, some of you may say that in the, for example, developmental psychology, there are people who analyze the contribution of 10 factors, etc. But that's not what I mean. I'm talking about experimental design like 10-way experimental design, 15-way or 20-way experimental design. And you never see that in our literature. That means it's impossible. So it's clear that traditional theory-driven design is fundamentally unfeasible for a comprehensive study. Therefore, we have to switch to a stimulus-driven approach. So let me contrast the two. The traditional theory-driven approach, we select a set of factors, we design stimuli to match those specific factors, and we collect data to test them. In the new stimulus-driven design, we do not start with a theory. We start to define a broad stimulus space. We sample randomly from that space, and we let the data itself review the important factors. In this example for visual working memory, the theory-driven design would have required us to predefine all relevant factors and their factorial combinations in advance, which, as I showed you, was unfeasible. The stimulus-driven design, on the other hand, takes a smarter approach. We first define our stimulus space as all possible four color combinations on a color wheel. So this is what I did. Basically, there are four colors, and then I randomly draw a color for each of them. So that all possible four color combination basically generate 10,000 example, 10,000 random combination from that space. That is our stimulus. No theory at all. Essentially no theory at all, like at the beginning. So you may be wondering, how can we identify any factors without predefining them? The answer is that we rely on the natural variations within the stimulus. This is directly inspired by AI. ImageNet did not predefine any factors for object recognition. Instead, it leveraged the natural variation present in millions of images. Similarly, in our CE approach, we did not predefine factors like trunking, yet the natural variation within our stimulus space was expected to capture such phenomena. In this example study, we simultaneously captured those factors, including all the classical factors previously known, along with a couple of novel ones, without needing to define a single one in advance. So that's what I mean. You start with no theory or minimum theory. You end up getting the best set of theory, the most comprehensive framework, theoretical framework in this area, which was not possible if you start with theory. So it should be emphasized that shifting from theory-driven to stimulus-driven design does not mean abandoning the goal of building theory.
Liqiang?
Sorry?
Can I ask a clarification, please?
Yeah, please.
Yeah, can you go back a couple of slides to the color wheels?
Okay, go back.
To the
Here?
yeah. I mean, color. I'm not in any way an expert in color, but color is continuous.
Yes.
And you sample colors randomly. You have to sample them from a discrete space, right?
Yes, like I divided those into 360 levels,
Okay.
which is a reasonable like
Okay,
resolution.
so there is some structure to the space. You impose some structure to the space from which you sample stimuli, right?
Yes, of course.
Okay.
Yeah.
Just to clarify. Yeah. Okay. Thanks.
Okay. Thank you. Okay, we are here. Okay, in C, theories are not the input, they are the output. Theory is destination, but not a starting point. So this is old way, theory-driven. And then the new way, we still care a lot about theory, but now theory is at the end, is not at the beginning. So we start with data, no theory, and we end up getting theory. Okay, so the second part is data collection. which is large-scale experiment. So this part is relatively straightforward. By large scale, so how large is large? Basically, in this case, 10,000 color patterns and 40 million responses and about 33,000 hours of data. That's a typical size of one of our experiment. We have a lot of not a lot, but about 10 ongoing projects, and each of them, some of them are slightly less, some of them slightly more, but generally between 20 to 40,000 hours of data. So here is the most important part, because many people, when they hear you have a large data set, they instantly think, okay, you are dealing with correlational observational data. It's no longer a controlled experiment. But I want to be clear, we are large-scale experiment. We are not correlational observational data. We are experiment. So even if it's large, it's still strictly controlled. Some people may be confused. What do you mean? You don't even have factor or theory predefined. So what do you mean controlled experiment? Controlled experiment here means that, of course, we don't have a factor in advance, but we do have conditions. So the responses are directly manipulated out because of those color combination. So in that sense, we can draw causal relationship between, there is a causal relationship between the pattern and the response. So in that sense, it's a controlled experiment, even if it's a large scale, like a data set, it's also controlled. Okay. And the third part is analysis. So obviously we don't have a theory in advance. Then we can't run predefined hypotheses. We have to figure out the conclusion by doing exploration. So that's why we need exploratory iterative model building. So how do we do it? For all of you, because the decision making is one of the area in which model building is the most popular. So I suppose all of you know this really well. So basically you have best model based on previous theory, and then from literature, from the pattern in the data, you draw another model, a new model, and then you do the model comparison, and then winner becomes the next best model, and then just continuously improve it. So, but we do differ from typical model development in the sense that our cycle is especially long. This cycle isn't quick. In this case study, the loop repeated about 1,000 times over 8 months. So basically, I tested 1,000 theoretical hypotheses in a sense. So it's critical to understand that while this process is data-guided, it remains rigorously theory-oriented. Every iteration explicitly tests theoretical hypotheses through formal model comparisons. Furthermore, this approach is explicitly exploratory, so it is not the same as the problematic practice of hacking. So hypothesizing after results are known. Now, this is known to be a terrible practice, but we are not that. What they do is they do exploration, but then they pretend they are doing hypothesis testing, and we do not pretend. We are clear and open from the beginning. We are doing exploration. Okay, you may think, okay, that's clear to say. But how about multiple testing problem? Testing 1,000 hypotheses generated after data collection would typically raise concerns about a false positive. Because people may think, okay, it's a red line. How can you do 1,000 hypothesis testing after data collection? However, our massive data set and the use of very strict effect size-based index, what we call CAD, ensure that all components of the model are highly reliable. This much. Unfortunately, I don't have time to elaborate on this index, but if you're interested, it's elaborated in that Nature Communication paper. And so basically, even 1,000 hypotheses is not a problem. I believe even 1 million hypotheses is not a problem because the data is so large and the standard is so strict. Okay, so finally, after all this, we reach a quantitative information processing model. So which, let me tell you a little bit. So, okay, so this is not so important because the main point here today is not working memory. So I will just go through it quickly. So basically, in this theory, we have different type of memory, like biased memory, pure guesses. Biased memory is like kind of like a Bayesian, bias. Pure guesses is like purely guessing. And the swap errors, you remember the color, you forgot the location. And of course, unbiased memory. And you combine all of those with 12 distinct components. And this, through 3 key phases. First, the pre-category processing, like items are first interact with each other before they are labeled. And then we label them and calculate the weight through a concrete process. And then we mix the responses. So this is the complete model. We are kind of running out of time, so I will be quick. Okay, so I have no time to elaborate this in detail, but I just want to tell you that although it looks complex, and it is more complex than typical theory, it is fully understandable if you're willing to spend, for example, 1 day on it. And then, okay, I also want to tell you 2 examples to show you that each step of this model can be understood. For example, at the beginning, we have this process to describe that kind of like a Bayesian. When 2 colors are very close, they attract each other, but then they're moderately close. They push away each other. They push each other away, and then we are really far, then they have nothing to do with each other. So we describe this with a Mexico hat-like function. So it's not just a function, it has a conceptual meaning. And okay, this is another example. I will just skip. Okay. So referring back to the PBS impossible trinity, the CE approach allows us to get breadth and precision, and then accepting some moderate complexity. So there is one last important point I want to make is that, so some of you may think, okay, this is interesting, but I don't care about complex models. I still prefer something simple, which is fine. But I want to tell you that this complexity does have a huge advantage. This precision breadth combination allows us to make accurate predictions. I suppose many of you care. At the same time, unlike neural networks, the complexity remains moderate, so the model stays interpretable. So that's the magic point here. Taken together, this may offer a viable solution to the explanation prediction dilemma in cognitive science. So what is that? So as many of you know that in cognitive science today, there are neural networks that make accurate prediction, but they cannot be explained. They are black box. On the other hand, there are psychological theories. For example, we have many theories of visual processing. We can understand them perfectly fine, but they do not make accurate predictions. So basically, there is this huge trade-off. You can either get an explanation or prediction, but not both. However, in this Nature Communication paper with working memory, this above example study serves as a proof that explanation and prediction can be achieved simultaneously. So to compare the previous classical model in the area with 4 parameter, this is its fitting. And so the fitting is NLL, but for our purpose, just when you go up, it gets better. And the neural network, I built a neural network myself with more than 30,000 parameters, which do much better in terms of making prediction than the traditional psychology model. But interesting thing is that this CE model. The CE model is only 57 parameters, which is more complex than this for sure, but it's not so much more complex, so it is still understandable. But then it is as accurate, and it actually slightly more accurate than the neural network. So that means, so the model uses 57 parameters and is fully interpretable, but it's at the same time exceeded the neural network. So that means we can, at least in some situations, combine explanation and prediction. Means psychological models can be as good as neural network. That's the message. If we're willing to be slightly complex like this. Okay, I also want to mention we are doing about 10 ongoing projects. 2 of them are related to, perhaps related to your work. In one of them, we're investigating the TSP problem, and we generate many location sets, and we're trying to explain like human performance. Another one, we are doing this taxis holds them as an experimental framework to investigate how humans infer event probability in complex uncertain scenario. As I'm sure all of you know, like people don't do this perfectly, but people do this reasonably well. But how do people differ from the like theoretical prediction? That's a interesting thing we can make predictions on, and we are modeling that. Okay, so both of these are still ongoing, and hopefully in 1 or 2 years we will be able to like publish those. So thank you, and here is a link to the paper if you want to take a look. And I also created a 19-episode video series on YouTube that explains this in detail. So if you want to know more details, please feel free to check this out. So that's all I want to say. Thank you very much.
Thank
Thank
you.
you.
This is great and very interesting. And now we open the floor to questions.
Questions?
So unless we have, yeah, David, go ahead.
So what do you mean, clarification, what do you mean by when you say prediction? What's the metric for prediction? When you say prediction, what do you call prediction?
You mean this particular case, right? Of course, in different studies, the prediction is measured in different ways. In this one, we use like a negative log likelihood to like
Of what? Of a test set? Of a different test set? Of what? What exactly?
On how like how the model explain human behavior, of course. Explain
In cross validation, in a split of train and test. What?
like how do we explain all those distributions? Of course, not just 4, like 10,000 of them. Of course, like we did try use cross validation, but it turns out because it makes so little difference, it's actually not necessary. But yeah, you can see that with cross validation. We did try that.
Yeah. Okay. So it's not an independent test set that you measure prediction on, right?
It's not.
It's from within the same experiment.
It's within the same experiment, yes.
Okay. Yeah. Okay. So one comment then that I have is that this is I think should be the next step, because prediction, real pure prediction should be about an independent set of results, not within the experiment. Because once you do this 1,000 iteration model building, you know the results during this iterations, these many iterations. You learn the results of the data. You learn the data as a
Yeah.
researcher, as a developer of the model. You develop your own understanding of what's going on in the data.
Yes.
So you see the data, then you build a model. So it's not very. So it's nice that it's fitting well, but it's not necessarily meaning that it's going to predict the new data well. And I think this may
Uh,
be the next step.
we do the. I mean, of course, we have access to the whole data, but we do verify it with cross validation, like train it, optimize this model on just part of the data, and then test it on the other part. And we did do that.
Yeah,
Yes.
but I'm saying that even in cross validation,
Yeah,
that would not be enough.
understand that. Yeah.
Even if it works in cross validation, it's not enough because when you develop the model,
Mm-hmm.
the best model, these iteration steps, you know the whole data set that you're eventually going to test on. So it has to be a completely independent, I think, a completely independent test set to say something about pure prediction. It has to be something that the data has never been used before in order to say something about whether it predicts better than a neural network or any other model for that matter. Yeah.
Yeah, understand that.
By
But
the way, that's the same problem with ImageNet. That's the same. It's not ImageNet is the same problem. Everyone's working on ImageNet, and everyone knows ImageNet now. Everyone knows what type of models work in predicting. I'm doing this ImageNet classifications, right? So you have to develop a model based on one data set, but you have to test it on another.
yeah, I understand that. But once you're absolutely right. But one thing I want to say is that if you try to play this kind of data for a while, you will get the sense that those effects are still so huge. So kind of like in physics, I don't know if they're doing cross validation or anything, or like in mathematics, like because it's something. Those are things that are so obvious, you wouldn't worry about that. They do not generalize. You see what I mean? Um,
Well,
like of course,
that's a point to show, I guess. But yeah, that would be more convincing. But yeah,
yeah,
thanks.
Thank you. David, go ahead, please.
Oh, great. Thanks. Can you hear me?
yeah, I can
Yes.
Yeah,
hear
yeah,
you.
yeah. Great. Really nice talk. Really interesting. Um, I wonder whether part of the problem here is about the quality of the data that we have. So you're looking at visual aspects of visual attention, and even in a specific area like that, the literature is huge, and there are just hundreds, thousands of studies, many of which show interaction effects, the effects of a moderator on some measure of attention. And of course, it's almost impossible to imagine a theory that would capture that data set. But maybe the problem is that 30%, 40%, 70% of this data is wrong because we're using completely inappropriate methods. We have insufficient statistical power. We have all of the issues that we know about in replication. And maybe if we could get rid of all the junk results that come from low power studies and just concentrate on the ones that are really credible, maybe we'd find it a bit easier to construct theories.
I'm sure that is an important factor, but like even if like for carefully chosen set of studies, I think it's still going to be difficult. Like for example, one thing I have tried to do that with myself. Like so I'm sure all of this data, where they are true data, where they come from, and I publish it. but nobody's going to read it. You see what I mean? Even if you publish, nobody's going to read it because it has essentially tens of conclusions, like maybe 50, 60 conclusions. In all those different situations, you got different things, and nobody's going to read it. So how is that going to help anyone? That's what I mean. So we need some index or objective index that tells us, okay, this is better than that. You see what I mean? So it's not just we can't build a complex theory. It's not we're not going to read a complex theory, myself included. Even if I'm angry that people don't read my theory, but I wouldn't read other people's 50 theory either. Yeah.
Whether or not people read it, I mean, the complex theory that nobody reads might be right.
Right. Yeah, but I mean, we couldn't move the field forward if nobody's going to read that complex but right theory. And I'm not sure it's going to be completely right. Like even if I try my best, there could be all kinds of things missing or like misinterpreted. So it needs to be a sustainable system that people can correct errors, like in the AI. They can build on each other. That's what I'm trying to propose here. Thank you very much for your comments. Thank you.
Andreas.
Yes, thank you very much for this talk. We had email communication about the project before, and I really appreciate the further explanations here. I think it's an interesting theory of science approach which you're taking here, just going from the other side, not starting from the theory, but starting from the data. And of course, it aligns with some of the approaches which we have in decision research, like this Patterson-Griffiths science paper on risky choices, and also the paper which we did with neural networks on collecting lots of data or random samples of data for probabilistic inference and then inferring the critical factors. So I think this goes a little bit in line, but it also, there's some, at least and so I think there's value going from both sides, going from the data and going from the theory. Why we often argue going from the theory side in judgment decision making is that in principle, you have a huge, if you have a 10-dimensional vector space of influence factors or 20-dimensional factors, what you are assuming, you have a huge volume of basically irrelevant tests. So basically you can do all of them and you can do random sampling of this, and then you have basically 90% of the choices. For instance, a choice, it would be something like you have dominated choices, A dominates B. Every theory predicts that you choose A over B. And then you have, let's say 80% of the volume in your 10-dimensional space includes such tasks. Then you can still do it, and at least you avoid the mistake that you lack something interesting there, which might be there. But in principle, most of the researchers would say we focus on the areas where something is going on, which is a little bit guided by theory. Basically, where the theories have different predictions, then you make the test for the different predictions. I think this is one of the reasons why we in judgment decision making often go more in this direction. Also, it's still interesting to go the other way around. So because then you might find something which is interesting and all people have overlooked, because perhaps there's something interesting going on in dominated gambles. I don't know, but perhaps it might be. This is one thing. And the other thing perhaps is that from this random sampling, or you propose random sampling, but random sampling of the vector space is not so easy. In principle, if you don't know, you say you don't think about the factors, or you don't use theory to think about factors, or to some degree you have to do it, because the problem is if you just sample somehow, often case that the factors will be correlated. And to avoid that, you at least have to identify which dimensions are the relevant ones and to orthogonize them to some degree, because perhaps in natural sampling, they might come together. Perhaps the interesting cases are relatively rare and are in some areas, so it's not that they're randomly scattered. And I think this then ties the two things together again. At some point, you have to include some consideration about the relevant factors, which is often informed by theory, and then to basically sample from that. Or perhaps you have different opinions on this, but perhaps this is just a comment or a question on what you think about that.
you're absolutely right. So it's in many situations, it's not self-evident how to randomly got the stimulus. And so why I say we don't start with theory, I'm more specifically saying we don't start with theoretical hypothesis, but we do have to consider those factors. So what is important? So I kind of believe that they should be the stimulus dimensions. Like they should be like, okay, use those to define the stimulus. So basically, I have to admit that when many of our ongoing projects, that is one major difficulty we are experiencing. We don't know how to do that truly randomly. And basically, but there we have basically two strategies. One is just to randomly draw from like real world examples. Let me give you one example, like a few weeks ago, and someone approached me and say he may be interested in study like the factors on how, okay, so what influence the part of the CV that someone will be hired. They have some theories, and he said, okay, with your like data guided approach, if you don't start with theory, how do you do that? Then I told him, like, okay, if we cannot come up with a perfect list of the theory, we start with the examples. Then we go online and find 10,000 real CVs and with real evaluations. So, and then we try to draw conclusion based on that. That could be biased or could be limited, but that's a one possible strategy. If that is not possible, then we have to go back to what you mentioned, lay out the possible factors and randomly draw from there. And there are always the risk that we're not doing it right. Actually, I will give you an example. Like, it not entirely a failure, but it's not well done because in one study we are trying to study the art styles. So what are the styles behind all the art? And then my student and I discuss that, and we figure out, okay, we would better start with real art, not like some arbitrary theory about style. And then what we do is we draw 500 most well-known painters, and then for each of them choose 100 representative like artwork, and we did that. But soon after we start data collection, like okay, we are after finish part of the data collection, half of that, we figure out we did this in the wrong way. Why? Because we rely on only traditional art, and then my wife, who is interested in like the animation or that related to her career, and then point out to me there is in the mid-journey, they already define 1,000 art styles, which is much broader than traditional art. And that's what we should have used, but it's too late. And if we get money to do another follow-up experiment, we will do that. I gave up this example, unsuccessful example, to tell you that we can only try to do our best. There's no guarantee what we did is sufficient or right. But I believe in any case, it's my sincere belief that it's much better than 2x2 hypothesis testing, like because it's by definition a much broader like approach, and it's both broader and precise in the sense that you can do formal modeling. Thank you.
Okay, guys, thank you. Unfortunately, we are running out of time, so the formal part is now over, and those who have to go are welcome to go now, and we will stay for a few more minutes for additional informal discussion and questions if we have those. Yeido, please go ahead.
Yeah, thanks. It was really interesting. You hear me okay?
Yeah, I can hear you.
Yeah, I have to go now, but I think that we are in our choice prediction competition approach trying to do something very similar to what you are doing. Basically, we did define a space, and then we looked at, I think last study was like 15 dimension or 11 dimension. And then what the main difference was that we challenged other researchers to come up with models, and we had a competition. Of course, our space is a little bit easier than yours, but it will be very different, very interesting to compare the two line of research because they're very similar. And it's great that I heard your talk, and then I will read and try to do that. I'm sorry that I have to leave now because I have some meeting now. So, but it was really interesting. I will definitely look at that. So thanks.
Thank you. If you have any comments, email me. Thank you.
Okay, I will. Thank you.
Thank you.
Bye.
David, please go ahead.
Yeah, so I wonder whether, I mean, so, you know, your example space, visual attention, yeah, it is a complicated area, but I mean, the question really is, how, you know, should we generalize from your particular domain to other ones? And I'm sure other people here might talk about, you know, theories of choice and so on. But I want to just mention, you know, theories about category learning. So I don't know whether you're familiar with the work of Rob Nozovsky. So what Rob Nozovsky did, going back to the 1980s, was to build a theory of category learning based on exemplars. It's called an exemplar theory. So you have examples stored in memory. And basically, when you have to classify a new item, you compute its similarity to the stored examples in memory, okay? Now, that idea turned out to be very powerful. And Rob was able to fit many data sets using that model of human category learning data. What's really, I mean, the reason that I'm mentioning this example is because what's happened since then is that Rob and his colleagues have taken that same basic principle and they have applied it to not just categorization, but also recognition memory, identification memory, working memory. You know, so the original theory has just grown and grown and grown, built on the same original principles, but it's, you know, every iteration it encompasses more and more and more data. And I mean, of course, the theory is wrong, like all theories are wrong, but I want to suggest that it's quite a strong counterexample to your rather pessimistic view about theory building in our field.
Is that a verbal theory? I have heard about it, but I don't know enough.
No, it's a mathematical theory. I mean, and it's all based around, you know, really excellent and well justified methodologies, such as using multidimensional scaling for determining the structure of the similarity space, all sorts of things. You know, I would say, you know, have a look at it. Rob Nozovsky, Nofsky. Super impressive. And to my mind, the best example in our field of an accumulating theory.
Do you think it's a complete theory, like it explains all the variance, or is it still just capture a major part of it?
No, of course it's not a complete theory. I mean, you come back in 1,000 years and we might have a complete theory. But I think it's a counterexample to your, you know, your general message, because it has shown that you can start from some very clear principles and build on those principles. Of course, when you apply the principles to a new domain, you have to make some assumptions. But you know, it's an example of how you can have accumulation, in my opinion.
I want to say that if we're just talking about theoretical notion that explains a large part or one part of the data, then there are also such things in attention working memory, like such as a resource or capacity, which like attention is a resource or capacities, which I believe in almost all the like attention related phenomena, you can apply that concept in some way. But the thing is that you have to, okay, for example, resource or capacity, you have to assume, okay, in this case, what is the effect of resource? So how it is constrained? It's not self-evident that like so let me put it this way. So not if we ask two graduate students to come up with a interpretation in a new situation, they wouldn't necessarily agree with each other. So and sometimes we have to try a few different ways. Okay, this way is confirmed. So this is how it should be interpreted in this case. But in my opinion, that is not a good enough theory. So do you agree that is not as good on the level?
Yeah. In that case,
Yeah.
I agree with that point. Yeah.
Yeah.
You know, things like resource, these are very abstract and, you know, flexible constructs. I don't think that's quite, that would be a fair criticism of the work that Nosovsky has done, but you might disagree with that. Yeah, thank you.
Thank you.
Andreas, please go ahead.
Yeah, so perhaps I also relating to David's comment just before. I think how you framed it, I think it's a good view on it. You certainly have positive examples of theory development where you make cumulative development or critical testing. What I propose, like let's say in the PLAT test, you try to make the critical test between the theories, and then you try to find out to basically get the maximum out of information gain. But on the other hand, what you suggest, and you said to use it in something like 20% of the research, going from bottom up, and I think it's nicely complementary, and it's very nice. Perhaps you also seen this paper by Mike Decay on the framing effect. I think is a good example here, which is very well known in this community. All the people have done framing effects, always with the same stimuli and all the time, and then thousands of studies. And oh no, he just did sample the whole stimulus space, and then he figured out, for instance, functional form issues, interactions, lots of interesting stuff on top of that. And I think this is just shows that going from both directions is, I think, has lots of value. Going from the theory has the advantage of being a bit more efficient in the first place, so you can test this particular thing and perhaps rule out whole class of models, or at least try to some degree do it. But you will certainly overlook some of these other interesting aspects which you try to investigate. And therefore, I think the combination of the two is really valuable. And it's really good that you highlighted the approach and to push it forward. I think we still have lots to learn also in judgment decision making. Even so, we think we have mapped out the space quite well already in some of the projects, like Ido already mentioned, and also in the risky choices and some of these. But I think there's still much more to do, and we discussed it briefly, perhaps also going a bit further down your road, like doing it perhaps a bit broader and with a few more factors in such an approach might also be valuable and might also be helpful for our field. So I'm now even more convinced than I was before that is at least on top of this, of our usual approach, it can be helpful, but it will not replace it. So this is perhaps more a comment than a question.
Yeah, to respond to your comments. I think I should make it clear, or I should admit that the way how I present this does not necessarily mean that I entirely do not see the value of theory or like a theory-driven study. But basically, as I said, like I believe that is already the dominant, dominant approach in the area. And so we need some change. So for the sake of change, at least, I believe we should start some, at least part, of this data-guided approach. I'm not sure, I think the field should be 100%, but I think 20% would be a fair, share that I argue would be healthy for the area. Of course, if I try to present everything balanced and in details, that would take 5 hours. And so I want to give you a simple message in this 40 minutes. So I just presented this very one-sided. Doesn't mean I'm so one-sided in my mind, but I do think this one-sided story is the best way to present it to you. Yeah, thank you.
Kineret, please go ahead. I think it's the last question for today.
Yeah, sorry, actually, Andreas also said many of the things, so I agree with you and with you both, I guess. I just think that, just maybe one more sentence, I think that in data collection there is theory. So you shouldn't be directed by specific hypothesis, but you should have theory of how to collect the data, which variables, and this is something that is kind of belongs to theoretical realm. But again, I agree with you that you don't need to specify the whole theory and then go. So in that, I don't think that. I think that you're right, and we should go and collect more data and then refine and think about the theories in a bit later. But there are a lot of theoretical parts in the data collection process. I think that's like what I meant.
Right. Okay, thank you very much for everyone coming. And
Thank you so much. Thank you
Thank
for
you.
very
Very
interesting
Thank you,
talk.
Shang.
And
Thank
you will hear from
you.
me. And see you in the next seminar, I hope so. Bye,
Yeah,
everyone.
I will try to come to some of them. Thank you.
Bye-bye.
Great.
Thanks.
Thanks.
Bye.
Bye.
See you.
Thank you.
Bye.
Bye.
Bye.